Stationary points are points where a function isn't increasing or decreasing, i.e. points where the tangent to the function is a horizontal line. Another way of putting this is points where the derivative of the function is zero. There are three types of stationary points: maximums, minimums, and points of inflection. Let's consider the following graph. We can see that this graph seems to have three stationary points: here, here, and here. The first is a maximum, and the last is a minimum. At a maximum, the function changes from increasing before the stationary point to decreasing after the point. At a minimum, on the other hand, the function changes from decreasing to increasing. We saw in the previous video that when we don't have a graph of the function, like we do here, we can find whether a stationary point is a maximum or a minimum using the second derivative test. Now, let's turn our attention to this third stationary point. Here the function doesn't switch from decreasing to increasing or vice versa. It is decreasing before the point, and it is decreasing again after. And what about this graph? Here we have a stationary point, where the function is increasing on either side of it. Such stationary points are called points of inflection. Now, say we're given a function and we want to find and classify the stationary points. We know that we can do the second derivative test. If we get a negative, it's a maximum, and if we get a positive, it's a minimum. So you might think that if we get 0, it's an inflection point. However, things are a little more complicated than this. If we get 0, it means this test didn't give us any information. So, what do we do when this happens? Well, let's explore this with an example. Show that the point 0, 0 is a point of inflection for y is equal to x cubed. Well, clearly 0, 0 lies on the curve, but let's check that this is a stationary point. If y is equal to x cubed, then dy by dx is equal to 3x squared. So, at x equals 0, dy by dx is 3 times 0 squared, which is 0. So the point 0, 0 for the curve y equals x cubed is a stationary point. But is it a point of inflection? Well, let's try the second derivative test. d2y by dx squared is d by dx of 3x squared, which is 3 times d by dx of x squared, which is 6x. So at x equals 0, d2y by dx squared is equal to 0. This point is showing us that the second derivative test carries no information. Were the second derivative positive or negative, we would know that we definitely have a maximum or minimum point. Because it's 0, we could have a maximum, minimum, or point of inflection. So we're going to have to examine the derivative on either side of the point. That is, we're going to decrease the x coordinate very slightly. Let's say compute dy by dx at x equal to minus a half, and then we're going to increase the x coordinate and compute dy by dx at, let's say, x equals plus a half. And then we're going to look at the values that we get. So, since dy by dx is equal to 3x squared, at x equals minus a half, dy by dx is equal to 3 times minus 1 half squared, which is 3 times 1 quarter, which is 3 quarters. At x equals plus a half, dy by dx is 3 times plus 1 half squared, which is 3 times 1 quarter, which again is 3 quarters. The important thing to notice here is that both values are positive. So, the gradient of the curve at points either side of the stationary point is positive. That is, the function is increasing on either side of the point. Hence, we can deduce that x equals 0 is a point of inflection.